Hello students, today I teach you complex number. It is complex number but it's not too much complex. You know about real number. Actually any number between to the real line is a real number, right? So what about complex number? Why we need a complex number? Okay, let's see. I take a quadratic equation. You know its solution. So it has two roots, real roots, that is x is equal to plus minus 1. So if we take another equation, so you can see that it has no real root. Any point in the real line can't satisfy this equation. Okay, let's see it. So it's not a real number. We define it as iota. We write it as I, but when we pronounce it is iota. Okay. So now come to the definition of a complex number. If Z is a complex number, it's of the form a plus ib, where I is equal to root over of minus 1 and a and b belongs to real number. Okay. So for real number, we represent in a real line. Now for any complex number, we represent it in a complex plane. Okay, we called it as a Argand plane. So let's see. This is x-axis, this is y-axis. So if a complex number is a plus ib, a is the real part of this complex number. That means it comes in the real line. Okay, so it is of the length a and it's the length b. So this is a comma b. So geometrical representation of a complex number in Argand plane, that is a comma b. Okay. So real part of the complex number real z is equal to a, and the imaginary part, this is the imaginary axis. So imaginary part of the complex number is b. You know what is I? I is equal to root over of minus 1. So come to some property of I, that is I. What is I square? I square is equal to root over of minus 1 whole square, that is minus 1. What about I cube? I cube is equal to I into I square. We know that I square is equal to minus 1, that is minus I. What about I4? I4 is equal to I into I cube. I cube is equal to minus I, that is equal to I into minus I, that is equal to minus I square. I square is equal to minus 1, that is plus 1. Okay, so for any power of I, that is I to the power 5 is equal to I to the power 4 is equal to 1, so I to the power 5 is equal to I to the power 6 is equal to I square, that is equal to minus I. So it comes as a cyclic process. Okay, so you can understand it. Coming the next part, that is very important. modulus of a complex number and argument of a complex number. Okay. Suppose z is a complex number a plus ib. So what is the modulus of z? We denote it as a mod z. Okay. It means the modulus of a complex number. So modulus of a complex number, actually it is the geometrical representation of a complex number a and b. So modulus of a complex number is the distance of that point from the origin. Okay. So this distance is the modulus of that complex number. So what is the distance? Actually this is a and this is b, right? And this is perpendicular. So this distance is root over of a square plus b square. So modulus of a complex number is root over of a square plus b square. Okay. Suppose a complex number is given 3 plus 4i. Okay. So what is the modulus of that complex number? So this is a, this is 3 and this is 4. So modulus of that complex number is root over of 3 square plus 4 square, that is equal to 5. Okay. So see one thing, if a modulus of a complex number is r, mod z is equal to r. Okay. So all the complex numbers whose modulus is r is actually present in that circle. Na? So radius of the circle is r. So all the point present in that circle, the modulus of that complex number is r. So if we particularize that angle theta, so we particularize a point, and this is the complex number. So this is a comma b is a coordinate of the complex number of a plus ib, and if we particularize r and theta, means the modulus and this theta, so we represent that complex number in another way. Okay, we call that theta is the argument of a complex number. Okay, so what about theta? Tan theta, you see that this is b, this is a, so tan theta is equal to b by a. Theta is equal to tan inverse b by a. So we call this theta is the argument of a complex number. This is the argument of a complex number. Okay, and theta belongs to minus pi to pi. So what is this? Actually we take the theta angle in the direction of that and in the negative direction of that. Okay, so that's why theta belongs to minus pi to pi. We don't take theta belongs to, we can take it to pi. That means in full cycle. Okay, but we don't take, means we particularize the argument as minus pi to pi. So we don't take it. Okay, we don't take it. Comes to example, we take two complex number, z1 is equal to 1 minus 8 and z2 is equal to minus 1 plus 8. Now we calculate the argument of these two complex numbers. Okay, so argument of z1 we take is as theta 1, that is tan inverse minus 1 comma 1, and argument of z2 is equal to theta 2, that is tan inverse 1 by minus 1. So in both cases, that is tan inverse minus 1. So the argument of z1 and z2, is it same or different? So let's see. This is, so z1 is equal to 1 comma minus 1. So that presents here. This is z1, this is 1 comma minus 1, and the z2, that is minus 1 1. Okay, so what about the argument of z1? So argument of z1, it is 45 degree, minus 45 degree. Okay, that is theta 1, and the argument of the z2 is that angle, it is theta 2, because we take theta belongs to minus pi to pi, right? So in both cases, that is tan inverse minus 1, but these numbers are different, that's why that theta are different.
Okay.